Hi everyone, in this video we are going to take a look at how Maxwell's equations predict the existence of electromagnetic waves. So we'll start from Maxwell's equations, show how to derive wave equations for the electric and magnetic fields from those, and then investigate some of the properties that those predicted waves must have. So I've started by writing out Maxwell's four equations. Under certain conditions, we're making the assumption here that we're in a vacuum. So there are no dielectric or magnetic materials around, and there are no source terms. In other words, there's no electrical charge and there are no currents flowing. So these are Maxwell's four equations in free space. Now, the first thing I want to point out about these equations is that the equations that I've labeled 3 and 4 are different from equations 1 and 2 in the sense that they involve both E, the electric field, and B, the magnetic field. And so our first task is going to be to do something about that. In other words, to try and rewrite equations 3 and 4 in a form that only involves one of the fields. The approach that we're going to take is basically take the curl of equation 3. The right-hand side will then involve curl B. We can then substitute curl B from equation 4 into equation 3 and thus eliminate B. You could do it the other way around if you wanted. You could take the curl of equation 4 first and then substitute curl E from 3 into 4, but it doesn't really matter. So let's have a look at how the details of that process work out. Okay, so as we said, we are going to take the curl of the entire equation 3. So the left-hand side will for now just leave as the curl of E. The right-hand side is, well, minus the curl of dB by dt, but the operator d by dt and the curl operator commute with each other, basically because it doesn't matter whether you differentiate with respect to time first or with respect to spatial coordinate first. And so I'm going to write the right-hand side as minus d by dt of curl B. And then we are going to rewrite both sides in a more useful way. So we need to use some sort of vector calculus identity. I'm going to quote this here. You can look up the proof if you'd like, or if you want to see me do a video on that, feel free to ask. But the identity we're going to use is that the curl of a vector field is as follows. It is the gradient of the divergence, in other words, written like that, and then minus the Laplacian of the vector field, like that. And what are we going to do with the right-hand side? Well, curl B, we can substitute from equation 4. We can substitute that in terms of E. And so the right-hand side is now minus d by dt of mu naught epsilon naught dE by dt. And we've already eliminated B, right? Now we've got an equation that only involves E. All we have to do is simplify this down and see what happens. Now you'll be able to immediately spot that we've got the divergence of E, but we know from equation 1 that the divergence of E is just 0. So that entire first term conveniently disappears. And the right-hand side, there's not really much we can do with that. Like mu naught epsilon naught is a constant. So this just becomes minus mu naught epsilon naught times d2e by dt squared. So if we just tidy that up, put all the terms on the same side, I'm also going to divide through by mu naught epsilon naught. You end up with d2e by dt squared minus 1 over mu naught epsilon naught times Laplacian of E is equal to the 0 vector. Now the reason I've written it in this particular form is because that's recognizable as a specific case of the general wave equation. So let me note this down. We've got a wave equation. It's a vector equation, right? So it's really 3 wave equations. Each individual component of the electric field oscillates according to the wave equation. But it's a well-established result that that coefficient in front of del squared E is the squared velocity of the waves, right? So we can say the speed of the waves, v, which is of course the speed of light because these are electromagnetic waves, so we can call that c, is 1 over the square root of mu naught epsilon naught. So we've already got our first very interesting result, which is this relationship between 3 fundamental constants, right? Speed of light and mu naught and epsilon naught. So far what we showed, right, is that each component of the electric field obeys the wave equation. Now, just to make that a little bit more concrete, let's actually write down an expression for the electric field that comes from that wave equation. And we're going to do this basically just by guessing a sensible solution and substituting it in. And we already know it's a wave equation, and so a sensible thing to do, as I've written here, would be to try a plane wave solution, and plane waves take this kind of form here. This E naught is kind of like the amplitude, but remember it's really a vector. So the three components of E naught are telling you the amplitude of oscillations of your electric field in the three different coordinate axes. And K is the wave vector. That tells you the direction that the wave is moving in. R is your position vector, and omega is the angular frequency. So this is a plane wave solution. Let's substitute that into the wave equation and see what happens. Well, with this second time derivative, each time you differentiate this thing with respect to time, you're just going to pull down a factor of minus I omega, right? Because you've got an I here, minus omega, and then that's all multiplied by the t. So if we do minus I omega times minus I omega, 1 for each of the time derivatives, you get minus omega squared. So that bit there is minus omega squared, multiplied by the original electric field, E. And what about this Laplacian? Well, okay, let's start by writing in minus c squared for this 1 over mu naught epsilon naught bit. The Laplacian, remember, is the second derivative with respect to x plus the second derivative with respect to y, and then the same for z. Now, if you imagine differentiating your electric field with respect to x, you are going to pull down a factor of ikx, right? I mean ik subscript x, where kx is the x component of your wave vector k. So if you do that twice, you get that whole thing squared, and I squared is minus 1. And so you get a factor of minus kx squared. And then, of course, identical method for the y and z derivatives. So I get minus ky squared minus kz squared, all of that multiplied by the original electric field, and that's supposed to be the zero vector. Now, the conclusion here is, I guess we can, we may as well change all of these to positive signs, because we've got a double minus. And the conclusion is, because both of these terms are proportional to the electric field, this thing here has to be equal to all of this if we want to get the zero vector. And we conclude that omega itself has to be c times the modulus of the wave vector k. That's come from square rooting all of this stuff. Like if you square if you square root kx squared plus ky squared plus kz squared, you get the modulus of k, right? So we've derived from our wave equation the relationship between angular frequency and the size of the wave vector. So we've got our plane wave solution for the oscillating electric field. Now we want to see how the magnetic field behaves and sort of investigate how the E and B fields are related to each other. Now there are different ways to do this. The approach I'm going to take is to use equation 3, because we already have an expression for E, so we could substitute that into equation 3 and then integrate it with respect to time to find the B field. So the first thing I'd like to do is find curl of E, given that we know that a solution for E looks like that plane wave. And so I'm going to write this as the curl of the vector amplitude E naught, and I'm going to abbreviate the complex exponential as e to the I phi, where it's sort of understood that the phi is k dot r minus omega t, just to save a little bit of space, save a little bit of writing. Now, E naught is a vector, e to the I phi is a scalar, and e to the I phi is really a scalar field because it depends on x, y, and z via the position vector r, right? So we're taking the curl of a vector times a scalar, and so we can use another vector calculus identity to do that. Again, I'm not going to prove this here. Let me know if you'd like to see a proof. But for now, I'm just going to quote that the curl of a vector times a scalar is the gradient of the scalar, right? So grad of e to the I phi crossed with the vector, which is e naught. And then we have to add on the scalar, which is e to the I phi, times the curl of the vector, which is curl of E naught. Now, something nice happens in this particular case because E naught is a constant and doesn't therefore actually have any spatial derivatives. So the curl is just 0, and we only get this, this first term here. So the next question is, how does the gradient operator act on e to the I phi, which is this bit here? Well, the gradient operator, remember, just the vector of 3 spatial derivatives. When we differentiate e to the I phi with respect to x, the coefficient of x, because of this dot product, the coefficient of x will be the x component of the wave vector k. And so the x component of the gradient vector will basically just multiply your original scalar by I times kx. And you can make the same argument for the y and z components, right? You differentiate e to the I phi with respect to y, you pull down a factor of I ky. Differentiate with respect to z, you pull down a factor of I kz. And so this gradient vector here is actually just equivalent to multiplying the whole thing by I times the wave vector k. So I can write that as I k e to the I phi crossed with e naught, like that. Now, because e to the I phi is a scalar and the cross product is linear in both of its vector arguments, it doesn't really matter whether we put the e to the I phi there or after the e naught. So what we could do is imagine putting the e to the I phi at the end, then you would have e naught e to the I phi, which is just the electric field, E, right? And so I can write this curl of E as I k crossed with the E vector itself. Now, what can we conclude from that? Well, we go back to equation 3. Equation 3 then tells us that the time derivative of B, dB by dt, is minus I k cross E, right? All I've done there is substituted curl E equals I k cross E, and then we can integrate both sides and say that the magnetic field B is minus I k crossed with the integral of the electric field with respect to time. It's pretty straightforward to do that electric field integral, actually, because we already know the electric field in terms of time. So let's go ahead and do that. So your B field is minus I k crossed with, well, we're trying to integrate that circled term there. The only time dependence is in the exponent in the form of minus I omega t. When you integrate an exponential like that, you end up just dividing by the coefficient of t. And so we're going to simply get 1 over minus I omega times the whole thing, e naught e to the I phi, like that. And the minus i's cancel, and we can tidy this up a little bit, write it as k crossed with e naught divided by omega times e to the I phi. Now, k cross e naught over omega, that's just some constant vector. So we could relabel that, and I guess for self-explanatory reasons, I'm going to call that b naught, right? It's like the vector amplitude of our oscillating B field. So let's call that b naught. It's defined as k cross e naught over omega. And so your magnetic field solution looks like b naught e to the I phi. And if we write phi in again, remember it's k dot r minus omega t. So we've concluded that since the electric field is oscillating as a plane wave, the magnetic field has to do the same thing. Now you can see from the fact that you've got the same complex exponential bit in your oscillating B field as you do in your oscillating E field, that implies that the magnetic field wave and electric field wave have the same wave vector and the same angular frequency, and that they're in phase with each other, right? So that's an interesting conclusion. But we can also conclude something else by examining this cross product here. So the other conclusion we can make is because B naught is just this cross product divided by omega, that the B naught vector has to be perpendicular to both the wave vector k and also the electric field vector E naught, right? we'll say a little bit more later on about how k and e naught are related to each other. But for now, we conclude that whatever k and e naught are, b naught is perpendicular to both of them because of that cross product. So let's just take a moment to summarize the key results that we've got so far. We've concluded that E and B both have plane wave solutions with wave vector k, angular frequency omega. The speed of those waves is the speed of light given by 1 over root mu naught epsilon naught, and omega and the modulus of k are related by omega equals c times mod k. And the electric and magnetic fields are not independent of each other in the sense that, well, firstly, they have the same wave vector and frequency, but also the amplitudes have to be related by this equation here, which tells us that the magnetic and electric fields are perpendicular, and also that the magnetic field is perpendicular to the wave vector. Now, the missing piece really is that we haven't said anything about how k and e naught are related to each other. There is another constraint on the behavior of these waves, which comes from equation 1, the divergence of E having to be 0. Let's consider what the divergence of E actually is, given that we know E takes this plane wave form. Let's write it down here. So the divergence of E, you're going to take the x component of E, differentiate it with respect to x, and then take the y component of E, differentiate with respect to y, and the same for z, and you're going to add all of those together. Now, when you differentiate with respect to x, for the same reasons that we were talking about earlier, you will pull down a factor of I k subscript x from that complex exponential. And so the first term in your divergence is going to be I k subscript x times the x component of E naught times your complex exponential, like that. And then we're going to get identical looking terms for y and z, right? So I ky E0 y component, same phase factor, and of course ikz from the z derivative, E naught z from the z component of E naught times e to the I phi. This can be written very nicely in compact vector notation as just I k dotted with E naught times e to the I phi. And equation 1 says that this is all supposed to be equal to 0. Now this phase factor can't be equal to 0, or is not identically equal to 0, right? And therefore k dotted with E naught must be identically equal to 0. And the conclusion from that, if the dot product of two vectors is 0, they're perpendicular, right? So E naught is perpendicular to k. And putting that fact together with the fact that B naught is perpendicular to both k and E naught, you conclude that the vectors k, the wave vector, and B naught and E naught, the magnetic and electric field vectors, they're all perpendicular to each other, mutually perpendicular. So if we were to draw that on a diagram, let's say your wave is propagating to the right, so your wave vector k looks like that, and your wave vector, your E naught vector, the direction of oscillation of the electric field is pointing up, then B naught would have to be either going into the page or out of the page. Or I guess I should say screen, into the screen or out of the screen. We can actually decide using this cross product here, right? K cross E naught divided by omega, and you can use whatever method you like the most to work out the direction of cross products. I use the right hand rule, which tells me that B naught should actually be coming out of the page like this. So they're all mutually perpendicular to each other. There's actually one final conclusion we can make about the nature of these waves, given all of these results that we've got, and that concerns the magnitude of E naught compared with the magnitude of B naught. Now, if k and E naught are perpendicular to each other, then the magnitude of the cross product is just the magnitude of k times the magnitude of E naught, right? And so from this circled equation there, you conclude that the magnitude of B naught is the magnitude of k divided by omega times the magnitude of E naught, right? There's no sine theta factor or anything because all of our vectors are perpendicular. But we also know from this circled relationship up there that modulus k divided by omega is 1 over c. So we conclude that the size or the amplitude of the magnetic field oscillations is the amplitude of the electric field oscillations divided by the speed of light, c, right? And so that's another constraint that these waves have to obey. Like the amplitudes of b and e are not independent of each other, and the ratio is always equal to c or 1 over c, depending on which way around you do it. So there you have it, a fairly comprehensive overview of properties of electromagnetic waves, showing how this all follows from Maxwell's equations. This is all very important and interesting stuff. Hope you've enjoyed watching. Thank you, and see you again soon.